and today we'll be demonstrating the molecule iodine trichloride, ICl3, using 4 theories. Each of them has their advantages and disadvantages that could be answered using another theory. I'm going to start by counting the total number of electrons in the molecule. So we should have 28 total. And now to draw the Lewis dot structure, because the shape doesn't really matter, iodine is going to be the central atom, and iodine is going to be the central atom, and here we have 24 electrons, and the remaining 4 electrons will go towards the central atom. For the Lewis dot structure, it doesn't matter where the electrons are placed on the central atom. They could be there, they could be here, but it doesn't really matter because this is a simple two-dimensional drawing that shows the bonding and non-bonding electrons. Okay. So the bonding electrons would have a bond with using a dash showing, and the non-bonding electrons would be the lone pairs shown here. Okay. This is an app simulation of the bonded atoms, so the lone pairs of the electrons are not shown, but they would be right here. This is also not a good demonstration of the angles because it looks very close to very close to a straight line, whereas that's not the case, and I'll go over that in the VSEPR theory. This is this is a progression of the molecule for ICl3. So we're gonna start with some iodine. This is another demonstration of using a 3D model of the electron geometry of ICl3. So 3 bonding atoms plus 2 lone pairs. That is a total of 5 electron groups. So that would lead to an electron geometry of Trigonal Bipyramidal. However, since we only have 3 bonding atoms, we're going to take away from the equatorial plane so that only 1 remains, and then the other 2 chlorines will be on the axial plane. And that leads to a T-shape, which is the molecular geometry. This is also a good molecule because a good model because it shows the orientation of the lone pairs. So one of them comes out towards the viewer, one of them goes away from the viewer. However, this does not show how the lone pairs affect the adjacent bonding pairs, which I will go over in the VSEPR theory. This app simulation does show that the angles between the lone pairs actually affect the adjacent atoms. So I told you before that that there isn't a straight line right here, but what actually is shown is that it kind of goes off to a distorted T shape right here. So it's very, very slight, but it is actually greater than 180 degrees. And because of that, this angle is actually going to be less than 90 degrees. And here my lone pairs are going to be facing it right there and right here. I'm going to draw VSEPR by hand. So in order to do that, use a ruler to draw a sort of T shape. This is going to be the long part of the T, and then instead of using a complete 90-degree angle, try to make it so that's slightly less, both on that angle and on this angle right here, and not too exaggerated. And then put the electrons as usual around each of the atoms in the molecule, except for the central atom. So the remaining two lone pair electron, the remaining 4 electrons would show as lone pairs right here, and you would label them as such. And then again, this angle right here is going to be greater than 180 degrees, and this angle is going to be less than 90 degrees. Now the reason that the reason that this area is going to be greater than 180 degrees is due to the VSEPR theory that lone pair repulsion is greater than lone pair bonding pair repulsion. So because these lone pairs want to be away from each other as much as possible due to the like charge, it's going to push away the adjacent bonding atoms. But it will push these slightly closer together compared to how far away that the lone pairs want to be from each other. So the advantages and disadvantages to VSEPR. We now have an accurate shape and angle prediction, and that could tell us the properties and the directions of the atoms. However, this does not show how the central atom iodine can bond to so many electrons at once. But we'll explain that using the energy diagram. So iodine has 7 valence electrons. You show them as being in the p and the s orbitals. So in the ground state, I is shown like this. However, in order for it to bond with 3 chlorine atoms, we have to excite So what that would look like is if I took this electron and excited it up to the d orbital because it's empty. So this is a promoted electron. And then in order to promote, you have to add energy. So I'm adding energy to that electron so that it can promote to the higher orbital. So now the atom has 2 lone pairs and 3 electrons available to bond. And I'm going to show how that looks like by first hybridizing these orbitals. You always got to circle which ones you're hybridizing. And now, when you're going to show hybridized orbitals, you're basically putting multiple orbitals together so that bonding can occur. Okay. So you have to make sure that the placement of the orbitals, you have to be careful of the placement of the orbitals. So I want to put, if I'm going to hybridize an orbital, I'm going to put it in between the P and the D, because it's higher, because my hybridized orbitals are going to be higher than the p orbitals, but still lower than the d. So I'm going to place 5 orbitals here and label them as my sp3d, because I have 1 s orbital and 3 p orbitals with my 1 d orbital. And then now I'm going to put my 2 lone pairs and my 3 electrons that are available for bonding. And then here are my 3 chlorines. They're all in the 3p, so I labeled them as such. I'm omitting the 3s and all those below. So to show the bonding, I'm going to draw ovals in between my hybridized orbitals and those in the chlorines. So now I'm going to label them as 3 bonded pairs between iodine and chlorine. And these are also sigma bonds, so these are sigma. And then here are my 2 lone pairs. And this is everything in black is the iodine in the bonded state. Now I'm going to draw the contour diagram. This shows how this is a visual representation of the energy diagram. Okay. So I drew the 4 atomic orbitals for my 3 chlorines and the iodine, and what I want to do is to bind them together to create a molecular orbital. So I'm just going to take my 4 atoms I'm going to take my 3 chlorine atoms and I'm going to going to push them towards the other electron right here. And I'm going to put them towards the electrons on the iodine, the red dots over here. So this area right here shows a shared electron density. So that's why they're overlapping. And again, this whole big angle is going to be greater than 180 degrees. And these are my 2 lone pairs. And this angle is going to be less than 90 degrees. And this is going to be a sigma bond right here, and right here. And then this is another app simulation showing the overlapping orbitals. So this is my shared electron densities, and it doesn't show, but here are this is where my 2 lone pairs would be. Okay, I hope this was helpful. Thank you for watching my demonstration of iodine trichloride.